So I will speak about waves and instabilities. That's something which is probably somehow narrow compared to other lectures you have here. But you will see that it's very broad range of problems we can have with fluctuations of electromagnetic fields in a charged medium, that means plasma. So here's my outline. I will start with music of the spheres. I will try to play some music also, so you will hopefully hear it. The question, if we can hear it, I will bring it up. I will show you also spacecraft measurements of electromagnetic waves, so you see already where it leads the music of the spheres. And these are names of different kinds of wave emissions we can observe by spacecraft in space. They have often names which remind people how they sound, because the first analysis of these data sets, some of them you may download from the Google Drive, where it was done by hearing. People just played the tapes sent down from the spacecraft and heard what's there, and they named the emissions after what they heard. So whistlers, plasmaspheric hiss, chorus, equatorial noise, lion roars, all that reminds what is the audible impression people first got from those recordings. If we have time, I will go to planets also and show you some recordings from different missions in the solar system. So you will see that there are similarities between observations we can do at Earth with observations done by automatic missions going to planets in the solar system and beyond, also outside of the solar system. So we will see how or hear how the atmosphere, ionosphere, plasmasphere, magnetosphere, and heliosphere sounds. So these are the spheres we will look at during this time. So I will start by quoting, and that's my first question, if you recognize from where it goes, from where it comes. It's a warm summer evening, circa 600 BC. You finished your shopping at the local market or agora, and you look up at the night sky. Who knows from where it comes? It's kind of history already. It was a series, Big Bang Theory, so it's from there. When Sheldon explained to Penny what Leonard does in his work, so it started by that. And I will start by the ancient Greece as well, namely Pythagoras, because Pythagoras looked up at the night sky also. I don't know if he was shopping at local market, agora, but for sure he looked at the night sky. And his school was the first people who started with the notion music of the spheres. And it's kind of poetic because they thought that everything in the universe, whatever it is, rock, objects, planets, sun, everything produces kind of sound. And you already try to hear the audible impression of it. Entire universe sounds in harmony, and that's music of the spheres. The problem is that we don't hear it because we're used to it. If you hear a sound which is repeating, you start not to get it into your brain after some time. So that's music of the spheres. It's everywhere, but we don't hear it anymore because we were born into it, and our brain already got used to it. So that's from Pythagoras, but there were some people after Pythagoras school mentioning music of the spheres, and namely Johannes Kepler. And that has connection with to my hometown, Prague, because Kepler did some part of his work on Kepler's law, describing the motion of the planets in the solar system, or from which Newton took his gravitational theory. So all the gravitation in the universe comes from these observations, which actually were not observations. Kepler wasn't observer. He just took data from Tycho Brahe, who was astronomer working in Prague, and he took the data and tried to make sense of it. And he actually made sense of it by assuming that everything is harmonious in universe, that there is some kind of harmonices mundi, celum harmonia. That's a copy of part of his book Harmonices Mundi. And in the 5th chapter of this book, you have the famous law, Kepler's law, describing the speed of orbital motion of the planets around the Sun. And that's something which was basis for Newton to derive the gravitational theory. So that's connection to my hometown, and also connection to Celorum Harmonia, music of the spheres. And here we have a sphere, kind of, you recognize it probably. That's showing you how thin the atmospheric layer is compared to the size of the Earth. You probably already contemplated that. We have only about 10 kilometers where we can breathe, where we can make sounds and hear sounds. 10 kilometers is probably too much for most of us. We cannot survive up to 8 kilometers even, but it's a very thin layer if you compare it to the dimension of the Earth. Who knows what is the dimension, what is the radius of the Earth in kilometers, or what?
6,400.
Yeah, approximately. Yeah, it's not completely spherical, of course, but that's the number we can compare the 10 kilometers or 8 kilometers of air we have, where we can make sound. So there is nothing we can do at larger radial distances, at larger altitudes. Now, you probably already noticed that there are some continents on this picture that comes from Deep Space Climate Observatory, which is from 2017. And this spacecraft took the picture from Lagrange point L1, which is between the Earth and the Sun, where the gravitational forces approximately equalize. And there is a place where you can place a spacecraft and look at the day side of the Earth all the time. It's approximately 1% of the distance of the Earth from the Sun, which is, who knows how far we are from the Sun in kilometers. Again, trying to get scales. 150 million kilometers. So it's 1.5 million kilometers from the Earth toward the Sun. That's where the picture was taken. And you see continents on it, and if you look closely, you can see my hometown of Prague right here. That's a small spot there. But you can also see Lisbon, where we are now. It's clear. There are no clouds. There were no clouds at that time. So what we can do to make sounds in space or record sounds in space, that's tricky because there is no air. We cannot produce sounds by speaking or loudspeakers or whatever means we do it on the surface of the Earth. But there are sounds, and I'll show you how to get them. First, how we can get them. We can send a spacecraft to the orbit above the atmospheric layer, and that's an example of a spacecraft. It's a small one. That was the first Czechoslovak spacecraft, Magion 1, which was launched nearly 50 years ago. So it's an old one. We still have spare model of this spacecraft at the Institute. So if you come to visit us or if you work with us, you can see it. It's in the lecture room. It's a small one. Weight is 15 kilograms approximately. Size is like a sheet of paper. But it worked to record electromagnetic waves in space. And that will be the kind of sound I will show you during my lecture. Did you Did any of you try to disassemble radio receiver? Maybe in your younger years? I did, and what I found was very similar to what you see here. Do you see the blue stick on the top of the spacecraft here? Anybody has an idea what it is? It looks like a detonator. It's not. It's not. Or handle. It's not a handle. You cannot. Our engineers who did that 50 years ago wouldn't like the idea that people could use it as a handle. That's a magnetic antenna. It's just a core with high magnetic permeability, which concentrates the flux in it, and wire around it, and you measure the voltage at the ends, at the two ends of the wire, which is induced by changes of the magnetic field in the core. So that's the principle of measurements, and the wire is hidden here behind the golden surface. So that measures the magnetic field fluctuations. And you know Faraday's law probably, so you need changing magnetic field to induce the voltage at the two ends of the wire. So it measures fluctuations of the magnetic field waves. The other part here are the silver sticks sticking out of the spacecraft. These are electric antennas, part of which was used to communicate with the ground station, receive commands from the ground station and send data down. And part of them, some of them were used to record the electric field. And the principle is that you have pieces of conductor on the two sides of the spacecraft, and you measure voltage between them. And if you have electric field, then you just divide the voltage by the distance of the two conductors, and you measure the electric field. And you can measure it as fluctuations of the electric field. So you can measure both electric and magnetic field out of electromagnetic waves by this. And I will show some data. I will show you some data here. On the top, you see as the time goes, that's the horizontal axis, you see volume. That's not calibrated here. It's just how the signal fluctuates. And that's recorded by this spacecraft in 1980, end of summer. On the bottom, the color figure shows you a dynamic spectrogram from those recordings. What does it mean for those of you who are not used to see those pictures? Horizontally, again, we have time, and vertically, that's frequency, going from 0 to slightly above 20 kilohertz. Question is if you can hear those waves up to 20 kilohertz. Anybody has an idea what the human ear can catch as frequencies? It depends on age, primarily. But you probably can hear waves up to 20 kilohertz approximately. So if there is sounds which makes 20,000 cycles per second, you will still hear it as a very high-pitched sound. In my case, I don't hear it anymore because as the ear gets older, it starts to cut the higher frequencies, higher pitched tones. But I can still hear those waves which are on the bottom of the spectrogram, units of kilohertz. And the color in the spectrogram shows you how intense the signal is at a given time, at a given frequency. So the higher you are on the spectrogram, the higher pitch sound you hear. The lower you are on the spectrogram, the lower pitch sound you hear. And the color goes from dark blue to red through yellow. So these lines would mean that you would hear constant frequency sound. If there is something which is changing, like this structure here, in time, in frequency, you will see some kind of whistling because it goes from higher pitch sound to lower pitch sound. like that. So I'll play it. And there will be a pointer, hopefully showing you where you are in time during that recording. Pointer is here. That was kind of history, 1980. Anybody has an idea what it was? What is the source of those whistling sounds you heard? Lightning. you know from where it goes, and those of you who downloaded my lecture already know it as well, because that's on the next slide. These waves are called whistlers. They whistle. You heard it. So they are called whistlers. And they come from lightning in the Earth atmosphere. So that's connection of the troposphere with space. And how it works? You have lightning discharge somewhere. You see it's not to scale. You have 6,400 kilometers radius of the Earth, and that approximately 80 kilometers above the surface of the Earth, the medium starts to be ionized. That means that from the neutral air you have here on the surface, you take electrons, negative electrons and positive ions, which are separated. So that's the bottom of the ionosphere, D layer of the ionosphere at approximately 80 kilometers above the surface. And as the medium is charged, it starts to react on electromagnetic waves. So if you emit waves from lightning like that, you heard the sound? That was the recording of lightning if you are very far on the surface of the Earth. It's called tweak. And that's property of the cavity between the conductive surface of the Earth and the conductive bottom layer of the ionosphere. So there is a thin layer, 80 kilometers high, all around the Earth, where waves from sources of electromagnetic waves can propagate and reflect from the ionosphere, reflects from the surface. And if they propagate far enough, they start to be deformed by propagating in that waveguide. And that makes those clicking sounds from lightning, because some frequencies are already suppressed by the properties of the waveguide. So we cannot, this way we wouldn't be able to get it to the spacecraft. Everything propagates in the cavity between the surface of the Earth and the ionosphere. But there is a trick. Earth has a magnetic field. So the magnetic field makes also frequencies which normally wouldn't penetrate the ionosphere. The critical frequency of the ionosphere is about, on the day side, is about 10 megahertz. So waves below 10 megahertz wouldn't normally get out. But as Earth has magnetic field, they can make it out. And if they propagate through the ionosphere, we can record them on a spacecraft. And Magellan spacecraft orbited at low Earth orbit. It means between, in this case, it was between 400 kilometers and 760 kilometers on an elliptical orbit. So at that close orbit from the surface, you can record signals from lightning, but not as that clicking sound or just one impulse, which is normally the signal from lightning. If you are close, lightning is very, very brief phenomenon. So you will get impulse which generates noise at all frequencies at the same time. That's normally the if you have analog radio and you have close thunderstorm, you will get disruptions from lightning discharges, which are just impulses. Signal noise at all frequencies, very short living. In the afternoon, Ivana Kolmašová will present you with more details about lightning and how the electromagnetic waves from it propagate. So I will not spend time on properties of lightning. We will go straight to space. So what you heard was recording on a spacecraft close to the Earth, and you may have recognized two kinds of sounds there. Longer whistling on the order of seconds, and then shorter signals which sounded like swishing or I don't want to go to the military type of analogs, but that was very, very brief sounding signals going again down in frequency, but very briefly. That's because you can catch signals from lightning just below the spacecraft. These were the brief ones. But you can also catch lightning from the other side of the Earth. And these were the whistlers taking several seconds to get down from high frequencies to low frequencies. That's because the property of the medium changes. If you propagate such a signal from lightning in the atmosphere, the speed of propagation is the same for all the frequencies. So the impulse from the lightning gets to you at the same time, approximately, on the surface of the Earth for all frequencies. But once you propagate the signal through the ionosphere, the dispersion starts to work, and that's the property of the charged medium. Waves at different frequencies propagate with different group speed. That's the important parameter here, group speed, because you have an impulse, you have an envelope which goes up and down in amplitude, and you need to propagate all that impulse somewhere. And now, if the medium is dispersive, different frequencies, different pitches of the sound get at different time to the receiver. At this range of frequencies, audible frequencies on the order of kilohertz, it works in a way that higher pitch sounds propagate faster than lower pitch sounds. So higher frequencies get first to you, and that makes the whistling sound because the low frequencies come later. And now it depends on the thickness of the layer through which you propagate, of the charged medium through which you propagate, how much dispersed the signal is. If you are very close to the source, you have only the ionosphere below you, so the dispersion is lower, and that makes the sound very, very quickly going down from high frequencies to low frequencies. If you propagate the signal along the magnetic field line all the way through the magnetosphere, you get larger dispersion, and that takes several seconds to get down from high frequencies to low frequencies. And that's the other property of the medium. The waves at those frequencies propagate mainly along the magnetic field. Not exactly, but very close to the magnetic field line. So that's why you can get signal from the other hemisphere all the way to the spacecraft or to the ground. And I will propagate it now from the other side. So from the northern hemisphere to the southern hemisphere, you can propagate along the field line. And if you have a receiver on the ground, you will hear that. So you don't need spacecraft to record whistlers. You can do it just by simple vertical electric antenna or magnetic loop on the surface of the Earth. If you are close enough to the field line, which leads you to the other hemisphere where a thunderstorm is at that time. So that's how the whistlers work approximately. They were explained in the 50s. That's not very historical explanation of those sounds. They were first recorded at the beginning of the 20th century by telephone lines. So, and it waited 50 years approximately to be explained. Yes.
Sorry, Professor. I would like to ask: is the frequency the only parameter we can use to identify this whistlers?
They are at the Earth, yes, and that's, I will speak about that a little bit in detail. That's the property of interplay between the frequency of the wave and characteristic frequencies of the plasma medium. So we need to be at a certain fraction of cyclotron frequency to be able to have that type of dispersion going from high frequencies to low frequencies. If you are higher, it goes oppositely. So that depends on the frequency, but at Earth, that's inaudible range of frequencies. At Jupiter, if we get to it, it's also audible. So
Okay, another question is, I mean, in an event where we have thunderstorm, let's say in the northern hemisphere and we have in the southern hemisphere, I mean, has there been any situation where we have a superposition of opposites traveling a whistler or something like that?
you just heard that. That was the superposition. If you still remember what was there, the slow dispersion whistlers came from the other hemisphere, and the very fast ones got to the spacecraft from just below it, from the hemisphere where the spacecraft was at the time. So that was the superposition of the two types of signals. So here are some equations. I don't want to scare you by them, but you probably know all of them. You know Maxwell's equations. I heard all of you have some physics background, so you at least heard about Maxwell's equations, and I hope you know how they look like. And this is a special shape of Maxwell's equations which are already modified for a harmonic signal. So if you have sinusoidal signal, and that's expressed here on the top as magnetic field composed from the static magnetic field B0 and then fluctuating part, and from this real part of the complex amplitude times exponential of imaginary unit times omega t minus k dot ex, that's wave vector is k, omega is the frequency, angular frequency, and that curl b is that rounded b is complex amplitude of the magnetic field. If you take real part, you get just cosine function. So that's harmonically fluctuating magnetic field superposed over the magnetic field of the Earth B0, which is static, doesn't change at those frequencies, at least. So if you insert that type of sinusoidal shape into Maxwell's equations, you get from the curl operator here in the Faraday's law. That's the first line. That's Faraday's law. Curl operator gives you k vector multiplication with the complex amplitude of the electric field. And what the complex amplitudes here mean, that you have amplitude of the harmonic signal, and the angle of the complex amplitude gives you the phase with respect to some zero time. So Maxwell's equations give you the first Faraday's law. These are just instead of differential equations, by inserting the harmonic signal into the Maxwell's equations, you get just algebraic equations, and it's easy to solve them. Ampere's law on the second line is symmetrical, and in a charged medium where we cannot assume that the currents are zero, we need to include them. So that's again complex amplitude of current, electric field, and if we were in the vacuum or in the air, which is close to the vacuum in that aspect, you wouldn't have currents. You would have just k cross E equal to omega b, and the k cross b equal to some factor times E, and that gives you speed of light propagation in the vacuum, or because we have the speed of light c here. Speed of light propagation in the vacuum or in the air approximately. But in a plasma, we need to take into account that there are charges which can move in the rhythm of the electromagnetic field. So if there is electric field fluctuating, changing its sign, the charges can move in the plasma. There's also magnetic field, so they cannot move straight. They need to go. They are influenced by the magnetic field, so they cannot keep their direction of motion, and all that should be included in that complex amplitude of the current. Now, we can combine the two Maxwell's equations into the wave equation, which again for vacuum gives you speed of light propagation, normal electromagnetic waves. In a plasma, we need to include the relation between the current and electric field on the right-hand side of the Ampere's law. And that's put together in plasma dielectric tensor, or dielectric tensor in general. In the plasma, we have plasma dielectric tensor, where we hide the relation between the current and the electric field. Once we do it, I will come back to it, how it is done. We can have just equation for the electric field, and you see it's an algebraic equation, so we can solve it. We have amplitude of the electric field, wave vector direction, that's kappa is just normalized wave vector by its modulus, which is wave number. Modulus of the wave vector is called wave number. It's in this case 2 pi over the wavelength. So it's connected to spatial properties because it comes from the spatial derivatives from curl. And refractive index of the medium is defined as the ratio of the speed of light and the phase speed of the wave. So propagation, and that's different from the group speed, of course. In normal vacuum or air, you have the same speed of propagation of the impulse and the phase of the wave as it propagates through the space. In a dispersive medium like plasma is different. The propagation of an impulse of an envelope of amplitude may go with different speed compared to the propagation of the wave itself in the impulse, the phase speed, and a different direction also, because the medium is anisotropic. Now, the refractive index is, as I said, ratio of the speed of light and the phase speed of the wave, which can be, because the phase speed is omega over a modulus of k, it can be written in this way as you see it on the screen. And now coming back to the relation of current density and electric field, it's very simple how we can do it. We can take just single particle and look how it moves without any interactions with other particles. It's called cold plasma approximation. We don't assume any chaotical motion of the particles. We just have them move in the rhythm of the wave and look how they react on it. And from that, if we have velocity of those particles, we multiply it by charge and by number density, and we get current density. So that's the relation how we can put together the electric field and the current density. Because for the speed of particles, we can just use influence of the magnetic field and the electric field on the particle, Lorentz force. Electric field and V cross B. That's where we put B0 here because the fluctuations are supposed to be small with respect to the background field. That's the approximation here. So now we have relation between the current density and the electric field of the wave. And if we put everything together, we can derive the dielectric tensor. And I spare you of calculations. If you want to do it, it's easy to do. We have everything here. So if you write your equations, you can end up with those expressions which are called Sticks parameters, according to the person who first derived them in the 60s. So those parameters R, L, and P have a meaning. The R and L may remind you right and left, which is true in this case. They mean right hand and left hand polarization. And P is from plasma because you have only plasma frequency. P symbol here is plasma frequency, which is related to the density of number density of particles. It's proportional to the square root of the density, meaning number of particles in volume. And some constants like charge, mass, and epsilon zero, permittivity of the vacuum. So plasma frequency is related just to the density. And that's, I was speaking about the critical frequency of the ionosphere, that's related to that. If you change the density of the ionosphere, the critical frequency changes, and the waves which can freely propagate out from the Earth can go to lower frequency if you decrease the density. That's here. The other characteristic frequency, which we already touched, is cyclotron frequency. And that's the frequency with which the particles rotate in the magnetic field. If you just put equilibrium between the centrifugal force and Lorentz force from the magnetic field and you throw the particle into the magnetic field, it will rotate in circle with a frequency which is proportional to the strength of the magnetic field, cyclotron frequency. So these are two characteristic frequencies. We don't need anything else for describing the propagation of electromagnetic waves in a charged medium like plasma. Putting that together, we have a matrix composed of those three Sticks parameters. All of them contain only the plasma frequency and the cyclotron frequency. S is an index showing you going through different particle species. So if you have plasma, you need to have at least two species of particles, one positive and the other negative, because plasma on larger scales is quasi-neutral or neutral. You have equal number of positive and negative particles in it. So you need at least two of them to form plasma, but around the Earth we have many of them because we have different kinds of ions, including negative ions. You sum those terms for all the types of particles, where you include their density and magnetic field, and you get to the matrix which describes you the dielectric properties of the medium. And as it is a matrix, it's dielectric tensor, not just dielectric constant. It's a dielectric tensor. It has to be a tensor because we are in anisotropic medium. We have magnetic field which controls the motion of the particles there. So we can design coordinates, and these are the three coordinates x, y, z, which are used here. You can design the coordinates in a way, for example, and that's usually done so that z-axis goes along the axis of anisotropy, which is along the direction of the local direction of the magnetic field, and the other two, x and y, are perpendicular to it, and you can rotate them around the magnetic field. Usually it is done in a way that x goes outward from the Earth at a given point. So you have Cartesian coordinates, and in these coordinates we have three components of the electric field, which are multiplied by the dielectric tensor, and that goes back to the wave equation. And here it is already with all the terms we need. These are the Sticks parameters S, D, and P, which are composed from the sums I showed on the last view graph. And we have matrix times three components of the electric field equal to 0. So we have homogeneous equation. Yes?
Sorry, Professor. Yeah, so from the previous slide, so when we make cold plasma approximation, it's only the paramagnetic field that influences the waves. Is that what you're saying in the...
Yes, we have a magnetic field, and that's the magnetic field which is embedded in the plasma. Typically, around the Earth, we have approximately dipole field, so wherever you are, you have very strong magnetic field generated in the core, but it doesn't change. It's still there at a given place. Of course, it changes if you go farther out from the Earth, but that's the approximation we work with, and the scales at which it doesn't change need to be compared with the wave frequency. So if you have waves at frequencies of hundreds of hertz, kilohertz, the background field doesn't change at those frequencies. So that's B0, and that makes you axis of anisotropy of the system. And then other important parameter is the density of the medium. It changes. You have denser regions around the Earth or more tenuous regions. So the magnetic field is reflected in the cyclotron frequency, the plasma density is reflected in the plasma frequency. These two frequencies are sufficient for each particle species, of course, because you have densities of the particle and mass here and charge. So for every type of particle, it's different. So we have you can immediately see that if you have protons and electrons, the cyclotron frequency of the electrons would be higher or lower than for protons. If you look here, is it higher or lower? Just a question to everybody. For protons, is higher than for electrons, or vice versa? It's higher, yes. How many times approximately? That's a tricky question.
I think it's because the mass is smaller in electrons.
Yes, yes. Mass is more in electrons. How many times compared to protons? 1,300 or so. Yeah, okay, you can make it to 2,000. So approximately 2,000 times lower frequency, cyclotron frequency for protons than for electrons. And that defines properties of the waves because you see it reflected in all the equations which we need to solve to get, for example, the group velocity or phase velocity at a given frequency. So that's the cyclotron frequency. And for plasma frequency now, if you have protons and electrons, for which type of particles of those two is the plasma frequency larger?
Sorry, what's the question?
We were speaking about cyclotron frequency, and the conclusion was that for protons, cyclotron frequency is 2,000 times approximately lower than for the electrons. What is this relation for the plasma frequency between the ions and protons and electrons? That's the simplest plasma we can get from hydrogen. Just tear the electrons out of the hydrogen atom and have protons and electrons, which is the most abundant plasma in the universe, of course, from hydrogen. Not around the Earth. If you go to the orbit of Magellan, we have mostly oxygen, so single ionized oxygen, with other species as well, including hydrogen. So what is it for the plasma frequency? You see charge, that's the same. And if you have protons and electrons only in the plasma, their number densities need to be the same. So n times q squared is the same for both. What is different is the mass. Mass is again 2,000 times lower for electrons than for protons. But you have square around the plasma frequency symbol here. So it's approximately 40 times. Plasma frequency for protons is about 40 times lower than for electrons. All right, did I answer your question or did I derive completely sideways?
Perfect.
Okay.
Thank you.
So what we have here finally, if we combine everything together, is just a homogeneous equation for three components of the electric field. And you immediately see that you cannot know what is the amplitude of the wave, because if you multiply this vector of electric field by whatever constant, you get the same equation again, because 0 is on the other side. So you cannot solve it for the amplitude. You only, from this equation, you can only get relations between the different components of the electric field. And if you go back to the Faraday's law, which relates electric field to the magnetic field, you get the magnetic field of the wave immediately. So you describe the electromagnetic field which propagates through the plasma with all the components you can measure. Now, if we come back to that wave equation and you try to solve it, you get the dispersion relation, which n is the refractive index, remember, that's what we defined, that's the ratio of the speed of light to the phase speed, relates the refractive index with the frequency of the waves, plasma parameters, meaning the cyclotron frequency and plasma frequency, and the angle theta, which is the angle as it is shown here between the wave vector and the magnetic field. So it depends, everything depends on the direction of propagation of the phase of the wave. That's the propagation of the phase. If it goes along the magnetic field at an angle or perpendicular to it. So that's angle theta here, which comes from the wave equation, from the double vectorial product you have there. So if you want to solve that equation, of course, you need to put determinant of this matrix to 0 to make the equations dependent, and that's actually the dispersion relation. That's the relation, that's the equation coming from putting the determinant of that matrix to 0. And you can solve it. You see, you have quadratic equation for square of the refractive index. You can immediately solve it, and you know, that's quadratic equation, so it can have 2 solutions, or 0 solution, or 1 solution, depending on the constant A, B, and C. Examples: if we propagate the wave along the magnetic field line, we have 2 solutions. Not always, but in a certain range of frequencies, we have 2 solutions. One is n squared refractive index equal to R parameter, and the other is equal to L parameter. Those modes are called R mode, right-hand polarized, or L mode, left-hand polarized. Now, if you remember from the optics, you always define the wave polarization looking at the wave vector, which way it rotates, which way the electric field of the wave rotates. In the plasma physics, we do it differently, because everything depends on the direction of the magnetic field. So if the wave field, electric field rotates, that might be important for your practical session after the break. If the wave rotates the same way as the electrons, you know how the electrons rotate. If you have magnetic field going, for example, down, which is approximately the case here, where is north? Where is north here? Anybody knows where is north? Sun is so supposing north is somewhere there. So we have magnetic field going down this way, obliquely. So, but we will assume for this example that it goes vertically down. If you have magnetic field going vertically down, which way the electrons would rotate? Do you know how to do it? You use right hand for it. You can use also left hand. It's called Fleming's rule. If you put current with your fingers, magnetic field going vertically into your palm, then the thumb shows you which way the particle diverts. So if you have, what did I say? Magnetic field going down, then the ions would rotate this way because they go as the current. The electrons would rotate this way. So these are the 2 modes actually. R mode rotates as electrons, L mode rotates as ions. And it doesn't matter if the wave goes down the field or up the field, they always rotate the same for the same mode. So that's very different from how we define sense of polarization in optics. Now, another example. If we propagate the wave perpendicular to the field line, we can get also 0, 1, or 2 solutions. And if we get 2 solutions, these are the 2 solutions, extraordinary mode and ordinary mode. Ordinary mode is the same as if we propagate the wave through vacuum, or through, not vacuum, through plasma without magnetic field. It means that the electric field of the wave fluctuates along the magnetic field line. The particles move along the magnetic field line freely. And the solution is n squared of refractive index equal to p parameter, and that was only plasma frequency in it, you remember. So that's the case which is exactly the same as plasma without magnetic field. Extraordinary mode already contains R, L, and S parameters. All of them contain the magnetic field, cyclotron frequency. So that's the mode which appears only in the plasma with the magnetic field. And that's, again, another type of propagation. If we take now the solutions of for the refractive index and insert them back into the wave equation, we can get relations of the components of the electric field. And from that, you get the right-hand polarization, left-hand polarization. For O mode, electric field goes along the thin line. In the X mode, electric field rotates elliptically, changes the amplitude during the rotation perpendicular to the thin line. And the same for the magnetic field. Inserting back the solution for the electric field into the Faraday's law, you get the components of the magnetic field. So if you combine everything together and you map the properties of the waves as a function of density and magnetic field, these are the two parameters, remember. Here, density is normalized by the square of the wave frequency. So that's plasma frequency squared over the wave frequency squared. That's proportional to the density, but depends on the frequency of the wave. And the same on the vertical axis, we have cyclotron frequency normalized by the wave frequency, which is proportional to the magnetic field strength, but inverse proportional to the frequency. Now, that's our parameter space. And in this parameter space, we can just very simply map the solution of the wave equation I just showed you and go through different parametric regimes of the plasma, how the waves propagate in there. Whistler mode, that's the mode you heard, is on the right-hand side here. And the symbols in this diagram mean how the wave actually propagates. Always in each region, separated by distinct lines in this space, density and magnetic field and wave frequency. You see a small picture which shows you how the phase speed of the waves reacts on the direction from the magnetic field. Vertically, we have direction of the magnetic field, so we have right-hand polarization. That was one of the examples I showed you on the previous slide. Right-hand polarization along the magnetic field and extraordinary polarization perpendicular to the magnetic field. And at all the angles between the two extreme values, you get polarization which you can calculate from the wave equation. It's not exactly extraordinary, it's not exactly right-hand, but it's something between that. And also the shape of this picture shows you what is the relation of the phase velocity parallel to the thin line and perpendicular to the thin line. It's larger for propagation perpendicular to it in this case. S equals 0, that's a line which separates two regimes of propagation of the waves. One below S equals 0 for frequencies. If you go with frequencies lower, you go to the right-hand side, up to on this picture, because it's always in the denominator. So low frequencies are on the right-hand side up. High frequencies are left on the bottom side. So if you go higher in frequency, you cross S equals 0 line and you get different type of propagation. Right-hand polarization along the thin line and no solution perpendicular to the thin line. So it only propagates in certain range of angles up to so-called resonance cone. And all the two regions in the parameter space we just described are for the Whistler mode. What you heard are the waves propagating in the Whistler mode, and they can be described by that type of polarization just very simply. It always fascinates me how simple the calculation can be to get to very complex result like this diagram, which is called CMA diagram, according to the people who first derived them, again in the 60s. And what is even more interesting on that, it's not only space where you can use this CMA diagram. It was actually all those three peoples worked in the fusion research. So in the laboratory experiments, people play with heating particles for fusion research. You have exactly the same diagram you can use, just the plasma frequency and the cyclotron frequencies are different. So it's rescaled. But in space, you can use exactly the same properties. Now, I mentioned that high frequencies are on the bottom left. So if you go above all the characteristic frequencies of the plasma with your fluctuations, it means the electron characteristic frequencies, because the electrons are the lightest species in plasma. If you go above the plasma frequency of the electrons, above the cyclotron frequency of the electrons, you already fluctuate so fast that the electrons are not able to follow. So the medium starts to be transparent. It's just like vacuum for the wave. And that's called free space mode. And you see Rx and LO, all three characteristic modes are in there. The larger frequency is, the closer you are to the origin of these coordinates, and the more similar the two ellipses are, they converge in a circle, showing you speed of light propagation with all the possible polarizations. So what is important for explanation of what you heard are the properties of the Whistler mode. S equals 0 line means lower hybrid frequency. I will not go into the details of that because we will spend all our time on it, but that's something which separates the two regimes of Whistler mode propagation. We will now go to the upper frequency part, it means lower on this diagram, and show you very approximately how we can get the whistling sound from this calculation. Now, starting with the solution for the refractive index, n squared is equal to the R parameter, that's propagation along the thin line in the right-hand polarized mode. That was the only one which was present in this part of the CMA diagram. And if you neglect ions completely, you assume dense plasma, then the sum here is much larger than the constant 1. So you can only use the right-hand part of this term. And neglecting the ions leaves you just with the electrons from that sum. So electron plasma frequency squared divided by wave frequency times cyclotron frequency of the electrons. And again, what we neglect is the frequency of the waves against the cyclotron frequency of the electrons. So we need to be sufficiently low in frequency, but not low enough to get ions involved. So for a certain range of frequencies, we can do that crude approximation for refractive index. So it's simple expression, and now we know that refractive index squared is wave number squared, speed of light squared divided by the Young-Grove frequency squared, and that's equal to our right-hand side here. So we can exactly determine what is the wave number as a function of wave frequency, and vice versa, what is the wave frequency as a function of wave number, and all those plasma parameters. Group speed is not omega over k, but partial derivative of omega with respect to k. So if you take partial, it can be total derivative in this case, of course. Omega with respect to k, from this expression we get 2k times all the constants here. And if we insert k, expression for k into it, we get an expression showing that group velocity is a constant speed of light, magnetic field, square root of the magnetic field, square root of the plasma density. So these are this is the constant for a given plasma setting. But what's important is that it's proportional to square root of omega. And now we are close to explain the whistling sounds, because group speed is proportional to square root of omega. Higher pitch sounds have higher omega, higher angular frequency. They propagate faster. Lower pitch sounds propagate slower, and if we transform it into the spectrogram type of curve, frequency as a function of time, we get the whistling sound from initial impulse at all frequencies at the same time. The relation of omega with respect to k is called dispersion relation, and you can draw it actually, what we have here. the tangent of this dispersion relation is the group speed. So that's another way how to look at it graphically. But the important thing is that group speed is proportional to square root of omega. That means the original impulse is dispersed into the whistling sounds we heard. Now, I will show you more examples just to get rid of equations for, yes?
Sorry, does that hold only for the Whistler phenomenon or for plasma in general?
That means
figure of, this exponential for frequency and time?
you saw that there are lots of approximations we made here. For example, we neglected ions, so it's not general. We cannot go to low frequencies with this approximation because ion starts to play a role. Also, we cannot go to high frequencies closer to the cyclotron frequency because we neglect omega with respect to omega electrons, omega uppercase electrons, so the cyclotron frequency of electrons. So we need to be low enough with respect to the cyclotron frequency in the wave frequency, but we cannot be as low as approaching the characteristic frequencies of the ions, like ion cyclotron frequency, or worse, the frequency which I called lower hybrid. That's in a dense plasma, lower hybrid frequency can be approximated as geometrical average of the cyclotron frequency of the ions and electrons. So it's approximately 40 times lower than the cyclotron frequency of electrons. And you cannot go too much close to the cyclotron frequency of electrons, so you have a range between cyclotron frequency of the electrons divided by 40, that's lower bound of the range, and you need to be sufficiently low with respect to the plasma frequency, to the cyclotron frequency of the electrons, meaning like cyclotron frequency divided by 5. If you go to cyclotron frequency divided by 4, it starts to be different already, the propagation properties. So that's the range of frequencies where it holds. But you see, it's a very simple approximation. That's for calculating, showing the derivation of the whistling sound, just that everybody can look at it. If you use the full expressions for the Sticks parameters and you put it in the computer, you can get everything in the CMA diagram very easily. And I have it on my phone, so you can plot the CMA diagram. If you download Python on your phone, you can calculate it on the mobile phone. It's not that computationally intense. So it's very limited range of frequencies, but you can derive easily other parts of the parametric space. Now, showing how much time do we have? We still have some time. Okay. Showing you more examples of it to refresh your mind from the equations now. You know how it works now, so you can enjoy the sounds. And these sounds will come from Van Allen probes. That was a NASA mission which is already over, 2 spacecraft orbiting the Earth, but at larger altitudes than Magellan did. The Van Allen probes were designed to investigate radiation belts of the Earth. And there is a very important class of waves called chorus, which is present in the radiation belt. I will show you some recordings of it later, which is in the same mode as whistlers, in the whistle mode again. Now, how it was measured, what I will show you. You see here kind of sticks on a boom connected to the spacecraft. Do you have any estimate what that could be? Just by analogy with Magellan. Yeah, this is antenna. Good guess. But these are actually the same principle of antennas as we had on Magellan. You remember the handle, the magnetic antenna. So that measured only one component of the magnetic field, because if you have high permeability core with winding of wire, you measure only the component which is along the core with approximately cosine pattern to the sides. Now, if you want to measure what I just derived in the equations, like polarization, for example, if the wave magnetic field rotates to the left or to the right with respect to the magnetic field, the same as electrons or ions, it's not sufficient to have just one component. You need to have at least one other component and then position the antennas exactly perpendicular to the magnetic field. And as the spacecraft orbits, the magnetic field direction changes. So we need the third antenna to be able to account for all the situations during the orbit. So these are the third antenna, 3 antennas. And that's usually done on the spacecraft, not always, but it's not very, very heavy. So you can get 3 magnetic antennas like that, measuring three components of the magnetic field. For the electric antennas, it's a little bit trickier because what you want to do is to have very long distance between the 2 conductors from which you measure the voltage between them. That's because you want to have strong enough signal not to be disturbed by other influences from the spacecraft, by the interferences. So usually what you want to do is to have tens of meters of the antennas, and that's not easy to hold. You cannot have those rigid booms there. So if you rotate the spacecraft and you stabilize it by spin, you can just by centrifugal force stick out wires with spheres at the end, and these are the conductors between which you measure the voltage, and you divide by their separation, you get the electric field. So for the electric field, it's easy to measure on a spin-stabilized spacecraft the components of the electric field which are in the spin plane, perpendicular to the spin axis, but it's not easy to get to the spin axis. You need a rigid boom there. It was done on Van Allen probes in all 3 components, but the rigid boom along the spin axis had data of a little bit lower quality than those in the spin plane. So on Van Allen probes, we had all 6 components of the electromagnetic field. And these are just 2 of them. Should be one component of the magnetic field, the other channel is the other component of the magnetic field. So all these, as it says, were whistlers coming from thunderstorms in the troposphere. Again, you will hear more about them in the afternoon. The signals we received were not so neat as we had them on Magellan. That's because the signal already propagates in the magnetosphere and can get to the regime where the assumptions of our calculation don't hold already. So the frequencies were large enough compared to the electron cyclotron frequency, and you saw it's in some instances that the dispersion turns the other way at high frequencies. So these whistlers can be also observed on the surface of the Earth. They are called nose whistlers because they have kind of nose signature on the spectrogram. And all those whistlers were also reflected in the magnetosphere. So you heard back something which you heard already, goes through the magnetosphere, reflects back to you, and you hear it again. Now, another set of examples. That comes from cluster project, some of the data of which I put in the data folder so you can play with it. And you again can see 4 spacecraft. Right now, we only have 3 of them because one of them, they are usually, we call them by numbers, they have also names, but we call them by numbers. Cluster 2 re-entered to the Earth atmosphere already last year. So we only have 3 of them now. They were designed to measure mainly the boundaries of the Earth magnetosphere bow shock, magnetopause, and the tail region, but they also measured in the inner magnetosphere, so they measured also whistlers, for example. 4 points in space allow you to measure the spatial properties of everything you measure there. So if you have 4 points in space, you can calculate the spatial gradients from the relations of measurements between the 4 spacecraft. I will show you some results of multi-point measurements in a while. But first, how it is measured again. So what you see here is a boom, at the end of which, again, we have 3 axial magnetic search coils. It's hidden here behind the golden thermal insulator layers, but it's in there. So these are the 3 search coils, and you can notice here there are some electric antennas sticking out of the spacecraft. Again, these are long wires, 50 meters long, which hold by centrifugal force on a rotating spacecraft. Each spacecraft rotated around its axis in 4 seconds. So they rotate quite fast. For Van Allen probes, it was 6 seconds. So it's also done for particle instruments, because if you measure particles, you can scan all the directions from where the particles come by just rotating the spacecraft. But it's also useful for electric antennas. On cluster, we didn't have spin axis antenna, so we only had 2 electric antennas. Unfortunately, we don't measure anymore, because after a re-entry of one of the spacecraft, the mission is still there. Instruments are working, but we don't get data from them. So now I will show you, this is the description of what I just did. Radio receiver, that's inside, and that's another part which I need to spend some time on describing it. On Van Allen probes, all the signals are connected to inside the spacecraft, where you have a receiver which takes the signals, samples them, puts them into the format which can be sent down through the telemetry to the Earth. The same was on cluster. On cluster, we had quite sophisticated instrument analyzing the phase relations and the amplitude relations between the 5 components, 3 magnetic and 2 electric components. But we also had one instrument which was built at the University of Iowa, which sampled just one single component of the signal. And that's what you get in the data folder also. You get sampling of 1 electric antenna for 2 types of emissions there. I will mention it later. But that's just, it works in a way that you amplify the signal and you look at it at exactly the same intervals all the time. And that's called sampling. So you have sequence of numbers sampled with time interval, which is inverse of the sampling frequency. And that's what you get from the receiver. You put it to the ground station, and we were lucky enough to receive it in our ground station in Panská Ves, which remained from Magion program. So we received signals from cluster from that wideband instrument, sampling the 1 component of the electric or magnetic field to the 2 antennas. Our ground people were able to receive actually 3 spacecraft at a time by 1 single antenna. If they were close, they were able to point the antenna beam into the 2 spacecraft and receive them at different frequencies, and the other antenna was on other spacecraft. And here's an example. Again, whistlers from lightning, but you see the part going down as with group speed proportional to the square root of frequency is at lower frequencies, and at higher frequencies starts to turn back. That's the region of frequencies where the approximation we used stops working. And again, you see reflections because the spacecraft are quite far from the Earth. And that's the same format as I showed before, waveform on the top and spectrogram on the bottom. Now, all the recordings I showed you up to now were either very close to the Earth, at low Earth orbit for Magellan, or in the dense plasma region called plasmasphere. And here you have a scheme. Yellow are the magnetic field lines, Earth in the middle, and the plasmasphere is a region which is organized along the magnetic field lines up to the distances of approximately 4 Earth radii from the center of the Earth. That boundary changes. That's called plasma pause, and it's variable, reacts on geomagnetic activity. If you have a long interval of calm magnetic field without any changes, plasmasphere extends, and you don't see any clear boundary where the density drops. If you have active times, plasmasphere shrinks, and you have very narrow region where the plasma density goes down to tens or units of particles per cc. So everything what I played to you was in the plasmasphere, where the whistlers are usually found. Now I will go to the aural region, and you have here an example of what you can see in the aural region. I will play you a little movie, which I actually took just on a simple camera, where we had cluster meeting of that cluster project in Norway. So you recognize Northern Lights aurora, and that's the region where you can, if you go up, you can and have a radio receiver and antennas there, you can record waves which are called aural hiss. So in the region above the aural field lines, where the auroras are formed, you can hear that. Of course, I say here, but that means you need to have electric antenna in this case, because this emission of aural hiss is usually only recorded in the electric field. It has a very negligible magnetic field component. And you hear that it's very different from whistlers. It's just hissing. It's banded, so there is a certain range of frequencies where it is recorded, depending on where you are. Again, I don't have time to go into the details, but these emissions are generated not by the electrons which light up the aurora, but by the electrons which go the other way. Electrons which go up, they are slower, and they can interact with plasma medium in a way that it generates Whistler mode waves, the same as whistlers, but very close to the resonance cone, very close to the angle where the wave stops propagating. And in that region, you can calculate it from the Sticks parameters again, by just cold plasma approximation. In that region, the wave has very negligible magnetic field, and the electric field is nearly along the wave vector. So that's the mode in which aural hiss propagates. Now, we have another type of hiss coming back to the plasmasphere, where, and that's still a mysterious emission. It's been known since the 60s again by the first spacecraft observations in the plasmasphere. It was captured, but we still don't know exactly from where it comes. There are different theories depending on time of publication and the actual setting of the research community. But some of the theories of generating the plasmaspheric hiss are from instabilities of the plasma inside the plasmasphere. Some of them explain them by influence of whistlers from lightning. Some of them explain them by influence from outer part of the behind the plasma pause of the magnetosphere, where chorus emissions, I will play to you, exist, and they can propagate inside and contribute to plasmaspheric hiss as well. So that's the mysterious plasmaspheric hiss. It's usually at lower frequencies compared to aural hiss you heard before. It goes up to 2 kilohertz usually inside the plasmasphere. Nothing that much interesting on those sounds compared to whistlers. But I will play to you some more interesting emissions which are related to radiation belts. They were discovered by James Van Allen, who put an instrument on the first US spacecraft, Explorer 1, and they saw radiation. They put just Geiger counter on that. We had a Geiger counter on Magellan as well, but that was a little bit sooner, Explorer 1. So they put Geiger counter on the spacecraft, and they saw radiation in space. And that was the discovery of inner radiation belts. We now know that there is a region where we have strong radiation close to the Earth, and then there is another outer belt. They are located at several Earth radii from the center of the Earth. The outer belt is very variable, and it depends also on the wave emissions, which I will play you now, because it was shown relatively recently that those waves in the Whistler mode again, but generated in the plasma, in the magnetosphere, not by lightning, but by plasma instabilities, can accelerate the electrons in the radiation belt. So they contribute to the radiation in space as well. So I will show you now emissions called chorus, which are usually observed outside of the plasma sphere. They mostly occur in high intensities on the dawn side, on the morning side. And they were also observed at the Earth. Before the spacecraft data came down, the same Owen Story, who explained Whistlers, also in this paper from the 53, he explained the observations by the ground antenna of waves which sound like birds in the morning. If you have nice morning, you sometimes hear birds singing. That's the sound you will hear now in different modifications. So it was called dawn chorus because of that similarity. And the fact that these waves are usually observed on the morning side, but they are all the way around the Earth. If you go to the noon side and you use spacecraft observations instead of ground antenna, you see them nearly all the time on the day side around noon. On the morning side, they are more intense, but you see them also on the night side and on the day side. And now they can be generated in different regions of the magnetosphere in different distances from the Earth. And that means if you go at different distances from the Earth, that the cyclotron frequency changes. The strength of the magnetic field goes down with radial distance from the center of the Earth, with which power of the distance? Do you remember that? 1 over r cube, right? Yeah, that's it. So it's very strong dependence. If you go farther out from the Earth, you have weaker magnetic field, and as the magnetic field controls the cyclotron frequency, cyclotron frequency is directly proportional to the magnetic field, you have also lower cyclotron frequency. And if you have plasma instabilities which generate waves at a certain fraction of the cyclotron frequency, as everything is controlled by those plasma parameters like cyclotron frequency, also generation of those waves is controlled by it. So farther out from the Earth, you would expect to hear higher pitch sound or lower pitch sound in this case, if you are at larger radial distances than closer to the Earth. Lower pitch sound, yes. So cyclotron frequency goes low, wave frequency goes lower as well. So I will play you now 3 recordings at different distances from the Earth, starting closer to the Earth. So what you heard was chorus, of course, but the chirps you heard mainly were at frequencies between 2 and 3 kilohertz. Chorus is emission which is nonlinear. This is generated by nonlinear interactions of electrons with plasma. You need temperature anisotropy to generate them. And the nonlinear mechanism generates those those emissions changing in frequency with time, but the other way than whistlers. That's not dispersion, which plays a role here, but the generation of the waves. Lower frequency waves induce the electron motion, which then generates higher frequency waves, and that generates the one of, it's called element of chorus, one chirp you heard. And there is also other sound that sounded like insects in the background. That's at higher frequencies, 4 kilohertz in this case, and you again see elements in them. The boundary between the two parts of sound you heard is around the 1/2 of the electron cyclotron frequency, where the wave properties, propagation properties change, but also the generation of the waves changes. So the gap in the spectrum here is 1/2 of the electron cyclotron frequency at the equator, where the waves are generated. And the properties of the upper band and lower band are slightly different. Usually the lower band is more intense, as you just heard. Now, going farther out from the Earth. So this recording was by cluster 1 at 4.4 Earth radii from the center of the Earth, just outside of the plasma pulse. 5.7, you see it on the top, and the frequencies are lower. Again, you see on the spectrogram 2 bands, more intense lower band, a higher band as well, and lower pitch sound compared to the previous recording. That was by one probe A. Now even farther out, that was 8.5 Earth radii, already closer to the magnetopause. You recognize that the pitch is lower, and the elements are also longer. So we are at hundreds of hertz in this case, and again you see 2 bands. There are some theories already explaining the gap between them, but that's something which we cannot spend time on now. Show you some example of multi-point observations. We have about time, so I will probably not go to the planets unless you really want to go there. I can run through that very quickly, but I will show you first example of multi-point observations, and that's the example you have in the data actually. So we have 4 recordings from 4 cluster spacecraft. They were very close at that time of observation. So they were, each of them was at small hundreds to tens of kilometers from the other spacecraft. And they also see very similar spectrograms, as you see here. And you recognize chorus, of course. It's written on the top. Upper band, lower band, and if you look at the elements in the lower band, they seem very similar between the 4 spacecraft. Some of them are missing on one of them, on one of the spacecraft. The most similar ones are probably cluster 1 and cluster 2 in those recordings. And what we did with that data set, and you can play with the data as well, is that we compared as a function of separation between the spacecraft. With 4 spacecraft, you can form 6 pairs. So these are the 6 pairs. Their distance along the thin line, perpendicular to the thin line, and the correlation coefficient in the band corresponding to the lower band of chorus. And you see that it goes down with perpendicular distance. It doesn't react that much on parallel distance of the spacecraft. It goes down approximately as a Gaussian curve. And that determines the width of the source of those elements, of course. Sounds like that. Again. So I will probably skip that and show you just. I wanted to show you that, but I can do it after the break probably. I can do it after the break. I will skip through all that and show you at least some data from the planetary mission. starting by Voyagers. These were the missions, you can see it here, they were launched at the same time as our Magellan. And they are already out of the solar system and still working. The two Voyager spacecraft are traveling now outside of the heliosphere, already in the interstellar space. And how we can know that? We know it from different kinds of measurements, but first signals we had were from waves. Recordings from Voyager 1, and the waves you just heard were emitted at local plasma frequency. And as you remember, plasma frequency is direct proportional to square root of plasma density. So in this case, the plasma density needed to increase. The spacecraft already recorded waves coming from the interstellar space where the density is higher than in the bubble formed by the heliosphere. We'll skip that and go to the conclusions. No, that was too far. To the conclusions. You'll have overview of the lecture now. No, I'm here. So, summary. So what you just heard were recordings of electromagnetic waves of spacecraft, from spacecraft in space. All the recordings, of course, were audible frequencies. The only one which was a little bit engineered was from Voyager, because there is a time span of tens of years between the different recordings, so that was something which was changed already. But all the other sounds you heard were just as they were recorded. If you had antennas instead of your ears, you would hear that in space. We went through different types of emissions: lighting-generated whistlers, auroral and plasmaspheric haze, chorus, and I briefly planed you boundary of the heliosphere from Voyager mission. I skipped an advert to what we look forwards to. That's the spacecraft mission to Jupiter, which was launched April 23 and is now orbiting in the solar system. We have an instrument we built in our lab on it. That's to record electromagnetic waves at audible frequencies, exactly the same range of frequencies we were going through now. It's part of the large instrument recording all the types of electromagnetic waves led by our Swedish colleagues, and we contributed by an analyzer which takes signals from magnetic antennas and electric antennas and analyzes them on board. The spacecraft was successfully launched, as I said, went through one revolution around the sun, encountered the Earth last year in summer, and made a gravitational maneuver with which the spacecraft trajectory was turned nearly at right angle, and the speed was changed of the orbital motion. And this year, at the end of this month, at the end of August, it will go very close to Venus for another gravitational maneuver, and there will be other two gravitational maneuvers at the Earth. That's because the spacecraft is very heavy. It weighs 6 tons, and it needs to get to Jupiter. There is not much power in our existing launchers to get it there straight, so we need to use gravitational maneuvers, take energy from orbital motion of the planets, and during several years make it fly to Jupiter, where we are supposed to arrive, as you see here, 2031. So it takes 8 years to get there with different gravitational maneuver. The main target is the moon Ganymede, which I didn't succeed to show you waves from, but these seem to be quite similar to what we see at Earth, but none of the spacecraft which were there before recorded several components of the electromagnetic field. So JUICE will be the first one to get directions of the wave propagation and look for sources of those waves. So that was my last slide. Thank you.
Okay, then.
You can start to play with it now, and we can interact later also. I prepared 3 types of data. That's what you already can download, I suppose, from the Google Drive. So one data set shows you electron and proton whistlers. I didn't mention proton whistlers in my lecture yet, but that's the same principle as electron whistlers, just these waves are left-hand polarized, not as electron whistlers, which are right-hand polarized in Whistler mode, and they are below the proton cyclotron frequency. Otherwise, they look quite similar. They have opposite dispersion, which you can again calculate from cold plasma theory. And I'll show you example of it a little bit later. These come from Freya satellite. It was old Swedish satellite working at low Earth orbit, and whistles were recorded there as well. Another type of waves is equatorial noise. Again, I didn't have time to present it during my lecture, but these are waves below the lower hybrid frequency. You saw it in the CMA diagram that at higher frequencies above lower hybrid, the waves don't propagate perpendicular to the thin line. They only propagate up to a certain angle, resonance angle, and along the thin line with right-hand polarization. If you go below lower hybrid, you can propagate waves perpendicular to the thin line, and that's the mode where equatorial noise propagates. These are very low-pitch sounds, and they have structures in it. So you can look at different lines which reflect, imprint the source region of those waves. And finally, with Whistler mode chorus, that was the example I succeeded to play. That's from the 4 spacecraft measurements by 4 cluster spacecraft. Now, the Freya data you recognize by F4 in the file names. If you have the file names already, if you downloaded the files, you see them there. And these are the data which are 3-dimensional. So you have 3 components, X, Y, Z, which are already transformed in the coordinate system of the magnetic field. So the coordinates, just repeating it, go in a way that Z is along the field line, X and Y are perpendicular to it, and X is outward from the Earth. So these 3 components, you have each of them separately in a file. And all these are normal ASCII files. So you can just browse them, you can read them, whatever software you are using. I assume that you might be normally using different types of software, each of you, or you can work with Python. If you do it, you can work with IDL if you are used to it, another type of software. But these are ASCII files. You can easily read them into your programming environment. They always have a header at the beginning. I will probably only briefly mention it because the files are self-descripting. And always, if these are, for example, the Freya files, we have this. Each file is from one component, and at the beginning you have sampling frequency. And that's the frequency with which the waveform of each of the components of the magnetic field is recorded in discrete samples. So this is discrete recording of the time series of the of the three magnetic components. So sampling frequency, if you here have sampling interval tau, sampling frequency is 1 over tau. That's what you see at the beginning of the file. And that's important for you to make sense of the data. So each waveform file, including the cluster waveforms for Whistler, mode, chorus, you see the 4 spacecraft, the recordings from the 4 spacecraft there, and each of them has sampling frequency at the beginning, the same for equatorial noise. There are also files from 3 cluster spacecraft which contain spectrum matrices. And I will just briefly go through what you can do with that. With the waveforms you can play, you can do FFT, fast Fourier transform on it. You can do spectral analysis, but the simplest way you can work with them is just to read the data and look at the polarization sense. And that's easy to do because if you plot, I don't know where to put it, I put it here. If you plot Y component against X component for a short time interval selected out of the spectrogram, as the time evolves, you can see different points rotating in a slightly chaotic way, but you can recognize the sense of rotation. And you remember for electron whistlers, the whistlers you heard in my lecture, you would expect the wave electric field or magnetic field, that's the same, in this situation, to rotate in the same sense as the electrons. And you can either use your left hand or right hand to figure out which sense it is. Left hand Fleming's rule, right hand Ampere's rule. You can imagine which sense it should rotate, because the magnetic field is always, the coordinate system is set in that way that magnetic field goes along z-axis out of the plane here, parallel to B0. And that's called hologram. So you can plot in whatever way you want that type of hologram and see if the wave rotates right hand or left hand. I will show you process data from Freya where you can see what you can expect where. You have it in the file as well. So that's the simplest analysis you can do. You can use your software, whatever it is, to analyze the waveforms in a way that you get power spectra out of it using fast Fourier transform. So in Python, you can just call library function FFT, fast Fourier transform. You can look it up. And what it does, I can move it a little bit. Is it movable? From the data file where you have samples, you can pass it through the FFT procedure and you get complex spectrum as a function of frequency out of it. So this is, for example, Bx, and then you get spectrum Bx, and that will be the complex amplitude which was used in the equations I showed you. So fast Fourier transform works in a way that first half of the complex numbers you get from as a result of it, you can use it, and that's representative for the spectrum. And these are complex numbers, so the squared modulus of that complex number you get at each frequency gives you squared modulus gives you power spectrum. And that's what I plotted on the spectrograms. I always took short interval of time did Fourier transform on it, and that gives you the power as a function of frequency in that short interval of time. Then I took next one and put all those columns one next to each other to form the power spectrogram. So you can do that as well. Now, if you have n data points in your waveform, the FFT returns you n complex numbers, but first half of that vector is just complex conjugate of the second half. So you can throw the second half out because it doesn't contain any more information that you get in the first half. So you take just n half of data, and each of the point is a complex number. So it has real part and imaginary part. If you get real part squared plus imaginary part squared, you get power. If you look at the angle of the complex number, arctangent bit imaginary over real part, you get the phase at a given frequency. So here you have a set of frequencies, and at each frequency you get power and phase of a given component. And now if you do the same with another component, you get also power and phase at each frequency, and you can construct a spectrum matrix. It's called spectrum matrix. At each frequency you can take different components, for example x, y, z components of the magnetic field, and you can construct a spectrum matrix by taking complex spectrum of x times complex conjugate at the given frequency from y, and that gives you sy, xy component of the spectrum matrix. You need to average that in time so that the random fluctuations go away, and that gives you one component of the spectrum matrix, and you can do it with all the combinations you have, and that forms you spectrum matrix 3 by 3 for 3 components of the magnetic field. And that's something you can then work with and do singular value decomposition of that spectrum matrix, and I'll show you how you do it. Here's a reference where it is described for wave observations on a spacecraft, so you have it in the file with a link. So now, what we can do with the spectrum matrix? The simplest way is to assume that the wave field is composed from one single plane wave. That's an assumption. It's not always the case in reality. But assuming that, you can throw that single plane wave into the Faraday's law. That's what we already did in the first half. And the result is that wave vector product with the wave electric field, and these can be complex amplitudes in the spectral domain, is equal to wave frequency times vector of complex values of the magnetic field, complex amplitudes. So that's already in the spectral domain. You need to transform the waveforms from the time domain, from measured sequence of samples by fast Fourier transform or whatever spectral analysis method you want to use, but that's the easiest one, into the spectral domain. And these are actually the complex numbers you get from the FFT. That's the complex amplitudes used in these equations, at each frequency separately. The frequency decomposition, that's easy. That's the fast Fourier transform which does it for you. But the assumption you need to add to it is that at each given frequency, you have wave coming from a single direction only, with one wave vector. And that's an assumption which is not always fulfilled. You can have waves coming from different directions at the same time. Now, assuming that, you immediately see from this equation that electric field needs to be perpendicular to the magnetic field. So if you if that assumption is correct, then you can have at a given frequency real and imaginary part of the magnetic field, real and imaginary part of the electric field, and they need to be perpendicular to each other, these vectors. The same for wave vector and the magnetic field. You see that K cross E is equal to omega B, so B needs to be perpendicular to both. And that's the equation we will use now. K dot B is equal to 0, that means both are perpendicular. Now, if you measure practically the three components of the magnetic field, you always have random fluctuations on that. So you can take all the information you get from the spectral matrix of three magnetic components, 3 by 3. That means real parts and imaginary parts. Of course, for the same component, if we do SXX, you have SX times SX conjugate, which gives you power spectrum of X. That's the same as S squared, the modulus of the complex number squared. So you don't have imaginary parts on the main diagonal, but you have real parts on the main diagonal only, and you have both real and imaginary parts in the cross-spectral components of the spectral matrix, where you don't have the same components involved. And this spectral matrix, as you see it from definition, is Hermitian. So that means that you have real part of the spectral matrix, and if you take the components above the main diagonal and below the main diagonal, they are complete conjugates. So real parts are the same, and the imaginary parts are just negative compared to the other triangle in the matrix. So you have minus imaginary part between component 1 and 2, and plus imaginary part between component 1 and 2 on the symmetric component. So it's Hermitian matrix, and you can that condition K dot B equal to 0 can be transformed into 6 equations. Real parts times wave vector dot product with wave vector is equal to 0, and for the imaginary parts the same. So we have 6 equations you can construct from the spectral matrix. This system is redundant. That's clear, because you have repeated information in that, but you can use it as a whole, because the spectral matrix from the experimental determination is always noisy, and the noise can cancel the more equations you use. Now, these are 3 components of the wave vector. Of course, we don't know the modulus of the wave vector from these equations, because you only have the condition that it's perpendicular to the magnetic field. So in fact, these are 2 unknowns. 2 angles which define the direction of the wave vector, but you don't know from this condition how large the wave vector is. You only know that it's perpendicular to the measured magnetic field plane. Now, how to solve it? There is an easy way. You can use your software again. In Python, you can find library function singular value decomposition, SVD. In other softwares, you have it as well. If you use IDL, it's there as well, SVD, singular value decomposition. And you can take this matrix 6 by 3 I just had on the previous slide and decompose it into the product of 3 matrices. One is again 6 by 3 rectangular matrix. That's this matrix U. Then you have diagonal matrix W and orthonormal matrix V, which defines you the coordinate system. That matrix W contains on the main diagonal the set of non-negative singular values, which you can order by magnitude, and you have 3 singular values which are very close to the decomposition of the spectral matrix into power in different directions defined by that orthonormal system. Now, how you work with that? You can singular value decomposition. You can use it as a black box. That's an iterative procedure. which is already well tested, and you can use it from your software package as it is. You feed it with the spectrum matrix A. You compose from real part and imaginary part of the spectrum matrix superposed over each other. And then you look at the diagonal matrix of singular values, 3 by 3 W, and you select the lowest singular value out of it. In theory, if you adjust a plane wave, it would be 0. One of them would be 0 if it is exactly plane wave. It's never the case because the spectral matrix is noisy from experimental determination. So you look at the minimum one, and corresponding to it, you select the row of the transformed V matrix that defines the coordinate system. And that gives you the direction of the wave vector. So it's a very, very easy procedure. Decompose the spectral matrix, select the minimum single value, and corresponding to it, you have the direction of the wave vector, which is already orthonormal vector. So one of the set of the orthonormal vectors, but it's normalized. That's what I meant here. So it's a normalized vector giving you the direction, and that's the direction of the wave vector. You can do more with it. You can look at the other two singular values, and the other two singular values give you the direction of the axis in the plane which is perpendicular to the wave vector, and that's the polarization wave of the polarization plane of the magnetic field. So you can, by the decomposition, you can also see what is the length of the two axes of the polarization ellipse. These are the two other singular values, the middle one and the maximum one. From the ratio, you get parameter which is called ellipticity. It's a little bit misleading because ellipticity equal to 0 means that the wave is linearly polarized, that you have just one singular value coming out from the decomposition, and then the wave is polarized in a single direction. It just fluctuates. It can be direction of the magnetic field, but it can be also, if you measure the electric field in 3 components, it would be direction very close to the wave vector for waves which don't have intense magnetic field. So it's 1 if the two singular values are the same. That means the length of the two axes of the polarization ellipse are the same. You have circle in polarization. So then ellipticity is equal to 1. What is usually done is that you take the ellipticity parameter, calculate it like that, and you multiply it by a sign which reflects the sense of polarization. You can get it from the hodogram, but you can get it from the cross spectrum between the X and Y component of the magnetic field. If it is negative, then the polarization is right hand. If it is positive, then the polarization is left hand. Electrons and ions modes. Another parameter you can calculate is to measure how planar the wave is. If in theory the smallest single value is 0 for a plane wave, then you take what you get from the decomposition as the smallest one, you normalize it by the largest one, and for noise it works in a way that you need to take square root of it, subtract it from 1, and that's parameter called planarity. If it is 1, that means that the polarization is concentrated in a single plane. You have 0 under the square root. If it is 0, that means that the minimum singular value is the same as the maximum singular value. You have polarization in all the directions at the same time. That's just non-planar wave in the extreme case, that the field is completely random. It's not concentrated in a plane. It's the same in all the directions. That corresponds to very random noise. So that's the analysis you can do with singular value decomposition, and that was my third assignment. You can choose whatever you want to do. You can play with the singular value decomposition. Those slides I just showed you are in the presentation, in both actually, in the presentation for hands-on session and in the presentation which I didn't succeed to finish, but it's there as well. So you can take it from there. You can play with feeding the spectral matrix into the single value decomposition. The files with the spectral matrices, these are the files which come from the cluster Staff SA instrument. That was the instrument which analyzed on board the spacecraft directly the signals coming from the antennas and constructed the spectral matrix on board. So that's what the spacecraft did, telemetred to the ground, and the spectral matrix is represented in the file. I think it's also self-descriptive. You can see the 3 components of the magnetic field, then 2 components of the electric field, so it's matrix 5 by 5. But as it is a Hermitian matrix, you don't need to show the entire matrix. You can show just the triangle above the main diagonal and the main diagonal, which is in the file. So you see on the first column, you see the main diagonal of the matrix. These are the power data in each of the components, of the 5 components. And then on the right-hand side of it, you see the cross spectra. That means the cross terms from first Bx, By, real imaginary part, and then it continues up to the electric field. So if you look in the spectrum matrix files. The waveform files are clear. They just contain a sequence of samples. And now I will show you what you should expect to obtain. First, Freya files, those with F in the name, in the file names. So you have 3 components there, X, Y, Z, in this coordinate system, in this green coordinate system. You can only look at 2 of them because the third one is along the magnetic field. X and Y components are in the plane perpendicular to the magnetic field, and you can see how the field rotates, if it is in the same sense as electrons or ions. This is an analysis of this exact time interval which you have in the data files. It's a wavelet analysis, but it shows you don't have to do wavelets here, but it shows you how the electron and ion whistlers take turn in the intensity. This is intensity or power spectrum on the bottom. It's very similar to what you saw in the power spectrograms before, just the frequency is logarithmic. And you have time going horizontally, electron whistlers whistling down like that, and then ion whistler, these are the blobs, intense blobs, which are connected to the electron whistlers. This sequence of lightning signals is very, very fast. So you have on the order of 50 milliseconds between the subsequent signals. Ivana will speak about that in the afternoon a little bit more. What is the source of those waves? But if you concentrate on the analysis of what is seen in the ionosphere, it's again, these signals come as you saw from Magellan. This is from Freya spacecraft, but the principle is exactly the same. You have lightning discharges very close to the spacecraft, right below it. So they propagate only through the ionosphere. They go very fast because that's easier for analysis. You only take short part of the waveform. You don't have to wait for several seconds for the whistle to make the whistling down in frequency. And you can see that first, at the beginning of the file, you should see the electron whistler, which is right-hand polarized. That means you need to see the rotation of the magnetic field in the same way as the electrons rotate. Then the intense part here is ion whistler, and that's left-hand polarized. The analysis on the top shows you the sense of polarization. In fact, that's the phase between the 2 components, X and Y. If it is plus 90 degrees in yellow color here, no, it's minus 90 degrees. These are proton whistlers. If it is plus 90 degrees, these are electron whistlers. So that's the phase between the 2 components of the magnetic magnetic field, one defining the rotation of the magnetic field in the same sense as electrons, these are the blue parts, and in the same sense as ions, these are the yellow parts. So at different portions of the waveforms, if you select just another time, you can get different polarization. For example, here at this time, around 225 milliseconds from the beginning, you get a very intense ion whistler, so you would see only left-hand polarization. At the beginning, you should see right-hand polarization for the electron whistler. So that's, and that's something which was published already. You have the reference here. You can look it up in the paper, how it was done there, but there are no more details about the data processing compared to what I just said. Another example, equatorial noise. We have files which have equatorial noise in the name, and they come from cluster spacecraft. 3 of them actually had the wideband instrument I was speaking about in my presentation on during the time when the 3 spacecraft passed through the equator. And that type of emissions is in the equatorial plane, and it stays there because, as I said, the mode is below the lower hybrid frequency with waves propagating perpendicular to the field line. And if they are generated in the equatorial plane and propagate with group velocity, the same as phase velocity in this case, in the direction perpendicular to the field line, they stay in the equatorial plane. So they are observed very close to the equatorial plane, and in this case, 3 cluster spacecraft with wideband instrument passed through the equatorial plane, and you see the coordinates here on this picture. Magnetic latitude is first negative on cluster 1, then goes to slow positive values, to low positive values, the same low positive values and higher positive values on the other 2 spacecraft, passing through the equatorial plane from the south to the north. These are dipole latitudes, so that means they are not exactly at the minimum B equator, which is a little bit shifted at these radial distances. It could be a few degrees from the dipole equator, so it's a little bit to the north. And you see always dipole equator and the equator where the field line actually reaches. If you go along the field line and you measure the strength of the magnetic field, and you go from the Earth, you have high magnetic field close to the Earth, and you follow the field line, you come to the point where the magnetic field goes down to the minimum and then starts to increase again as you come back to the Earth along the field line. So the minimum B equator, that defines the position of the waves actually. That's a little bit to the positive latitudes always in this case. So what you can do with this data set, you have always one component of data, so you cannot do polarization analysis, spectrometry out of it, but you can try to find the sequence of spectral lines in it, because these spectral lines, these are again spectrograms, time, frequency. These spectral lines are linked to the generation regions of these waves. They can be generated both in the plasma sphere and outside, and propagate in the equatorial plane. The frequencies which are in them are actually multiples of the ion cyclotron frequency. They are generated, again, I didn't have time to go into the details of that, but they are generated in so-called ion-Bernstein modes. These are modes which are spaced at multiples of the ion cyclotron frequencies. It can be protons, it can be helium as well. And they are generated in modes which you cannot get from the cold plasma theory. That's the exception. You can get nearly everything you observe from the cold plasma theory, not ion-Bernstein modes. For that you need to have hot plasma generating the waves which rely on the distribution of ions at finite temperatures with temperature anisotropy perpendicular to the field. But what is important that the distance of those lines shows you from where the waves come. from which radial distance from the Earth, because that's the ionospectrum frequency at the point of generation. So what you can do, you can just take the waveform of those equatorial noise emissions and try to calculate just line spectra. Here it is on the spectrogram, but if you integrate in time, you get the line spectra where the lines should appear at tenths of hertz separately, and then very fine system of lines at higher frequencies. These are the waves coming from the outer region of the magnetosphere. So, and on the top, that's what you don't get from the data, but again, it's described on this reference. These are results from onboard analysis of spectral matrices. If you take the spectral matrices and calculate power and ellipticity, I just described, for equatorial noise, it's very linear in the magnetic field. That's the signature of the extraordinary mode below lower Hebrew frequency, where the magnetic field is exactly along the thin line. You may remember from what I presented, electric field is in the plane perpendicular to the thin line for the extraordinary mode, elliptically polarized, but magnetic field is exactly along the thin line, linearly polarized. So the ellipticity goes to 0 in this case. So what you can get from the data is this system of spectral lines if you do frequency analysis. And finally, the last data set are the data from recordings from 4 cluster spacecraft. You heard that sound. This is chorus, very close to the source region, from 4 spacecraft. Again, you can do either frequency analysis, or you can just compare the power in the waveform as a function of time and try to calculate the correlation coefficients for between the spacecraft of power, because the lower band is dominating here, so you would see it there. So these are my data sets and the 3 assignments. I figured out what you can do. Don't have much time for it actually, but you can try to at least read the data and try to do the hologram if you want from Freya data. And if you have any questions, don't hesitate to ask. I can try to help you individually also. Or you can do, yeah.
Then we kind of finished and